Hello everyone, my name is Devin King, and I will show you how to perform a thermal power dissipation simulation on a FR-4 dielectric surface in ANSYS Icepak. When you open ANSYS Electronics desktop, click on the tab that says Icepak to begin your simulation. And this will be the image that pops up on your screen. You can see beneath your Projects tab, you now have Icepak Design 1 Steady State. In the image on your right, you have this region here. This region is the atmosphere and general temperature range of your design. Your next action will be to design a geometry inside of this region. You can remove the region by clicking on it and then choosing to hide it. Any geometry you create will still appear in the region. Now we'll begin creating material and then selecting which type we want. We go over to the prism block and we simply make a flat square and then we move upward. Now we have our model. It is the default material is aluminum extruded. We need a FR-4 dielectric. So what we do now, we select it and then right click, and here we can now reassign both the material and surface material. We'll start with the internal material first. There. Now as you can see, this is the materials menu. In here, you'll find the thermal properties of all material that comes within the ANSYS Icepak system. Thermal conductivity, mass density, specific heat, thermal expansion, thermal material type, thermal diffusivity, molecular mass, and dynamic viscosity. Now what we need is the FR-4 material. The fastest way to do that is to simply search for it. And see, it is already in our systems library, and it already has its information within the library of the system. So now it's highlighted, and we click OK. And there, now the material has changed. Next, we'll change the surface material. Repeat as the same, click, right click, but now we go to assign surface material. And for FR4, what we'd want is a copper polished surface. As we can see here, just even typing in C brings it up. And then we click OK. Now with this block, if you go to box 1, you can already see the information. Material is FR4, surface material is copper polished, and it is named box 1. We can click in this box and change the name to dielectric. And click OK. It has changed. Click on it again. You can see that. Now you go to Create Box. In here is where the geometry, such as this shape and position of the box, is held. In this section, its origin is at 0, 0, 0, basically the origin of the entire simulation. And its size, measured in millimeters, 0.7, 0.5, and 0.1. You can think X and Y as length and height interchangeably, but Z will always be the size. We can change this to something closer to a average size for a PCB board, such as a 2 millimeter thickness or height, We'll put 2.1. And as soon as you're done clicking it, you can see it instantly changes size. You can change its length and width, as we'll go by 10 millimeters. And in the X direction, we'll go by 15. As you can see, the image has greatly increased that we can no longer see the entire box. That can be fixed by simply going to Fit All. And there we have it. Now, it may look incredibly dense, but that is nothing to be worried about. Compared to other items on the box, this can be fixed easily. So now we have our board base, and now we're going to add the components that you would normally have on top. For this, we'll just create 4 simple blocks. Now, when you begin, you can already see that it's telling you at which point the boxes are being made. This is fine. Create a square and then a simple height. And if you click away, you will notice that we can no longer see the box, and similarly, that it's actually inside. It was built on the surface of the entire simulation is purpose for, but not on top of the box. We can fix that by going to the box that was recently created. You can see that it comes as aluminum, and going to create box. What we're going to do is we're going to change its position. This position is always the farthest bottom corner of any box. So if the height of the base is 2.1 meters, then we need to change this position to 2.1 as well. But you can also see, and if we rotate, it's still not on the box. So now we must move it forward. The red line is in the X direction, while the green line is in the Y direction. It's always X, Y, Z. And moving it in a positive direction moves it towards in the same direction as the arrow. And we'll move it 2 millimeters. And there we go. Now we have our first component, and we can bring it in from the edge just a bit. We'll say 2.5. And now that we have this block, we can also simply copy and paste it across this image. Stop rotating. We click it, right click, go to Edit, Copy, right click again, and then paste. Now, we still don't see that block, but they're actually overlapping each other. It was created as box 2. Now we go over to box 2, select that, and move it in the Y direction by another 2.5. So 5 millimeters. And there we have it, 2 boxes made out of aluminum. For now, I believe this is enough to form a power dissipation thermal simulation. What you'll do now is you'll select both boxes, hold Control, click, and then right click. Now you go to Assign Thermal. Select Block. Now you'll enter in the wattage of the power dissipated from the components. For now, we'll just go with 1.5 watts. Go over to your Projects tab and click on Icepak Design 1 to extend it. go to where you see thermal, and you'll see block 1. In properties, it highlights which blocks are assigned to this thermal configuration, and you see a total power of 1.5 emitting from both. Now we need to bring back the air region. You'll click on it, and you'll make it show by clicking on this eye with the green check mark. You'll need to zoom out. Next, if you see over here, it says select object. So when you select an object, it selects the whole system. Instead, we need to select it by face. You can do that by changing it here, or simply pressing the F key. Pressing O changes it back to object. Pressing F returns it to face. You need to select 2 parallel faces to create an airflow. The first face will be selected, then you right click, you go down to assign thermal, and this time you go to opening. Here is where we change the airflow. Ambient temperature is 20 degrees Celsius, as well as the ambient radiation temperature. You'll go and change it from pressure to velocity. And then, since they're parallel to the X direction, we'll change this to a airflow of 2 meters per second. This is what the MPR second means. And now we also have to do that to the back. We can select the back one by go to select by name, select region, and we can just cycle through until we reach our selected face. Now you right click and perform the same action. Assign thermal, opening, velocity, 2 meters per second. This is a measurement of velocity, so this means it'll flow in the same direction in the positive X direction. And then you click OK. Now we have our block and our openings. We can now perform a simulation. Before doing so, we go to simulation and we have to validate it. Validating will check for any errors such as 2 geometries that are intersecting, which will stop the simulation from occurring. Click validate, and as you can see, we already have 1 error. We have to set up an analysis before we do so. So come over to this tab area and right click on analysis and add solution setup. These are the number of iterations, and it will determine generally how long and how accurate your simulation is. So we can change this to, whoops, that's not what we wanted. We'll just call this Sim1. This is merely the name. It can be anything you need. But we'll change the iterations to around 150. We keep temperature and flow and change from laminar to turbulent, which will include random chaotic airflow, which is basically what turbulence is. Keep the radiation off and solve for flow and energy equations sequentially. Then we click OK. Validate again, and we're all good. Design settings to model, boundaries, monitors, mesh, and the analysis setup are fine. Close that, and now we go to Analyze All. Oh, and also we must save the product as well. You can save it if you have a specified menu or folder. We'll create a new one. File name project 1 and save. And now back to Analyze All, which will run the analysis instantly. And as we can see, it is now running in this project. progress bar. We'll come back to when it is done. Okay, it is now done and the simulation has been performed. We know this from this message, normal completion of simulation on local server machine. Now we need to actually see the simulation. Now, as before, we no longer need to see the region. You can go back to draw, press O, select the entire object, click on the region, and hide it. Now we go back to face. Press F, select the top of the board, right click, and now we need to plot fields. Go into plot fields to temperature. We want this correct, and then we just click done. And there you have it, a fine simulation of the board. Over here in the tab menus, it's under field overlays. Open it, it's in temperature, open it one more time, and then click here. Now you have a transparent view of the temperature. You can see here at these points of junctions that they're incredibly hot. This is due to no heat sink to absorb and pass on the thermal energy from these blocks. In the next video, I will show you how to design a heat sink for this system. Thank you.